So here's a quick recap of the reinforcement learning theory that we've been talking about, the super brief version. So first, welcome. This is, in terms of how to participate, we welcome comments, questions. Feel free to unmute at any time, ask a question. If you're unable to, you can put stuff, or don't want to, you can put stuff in the chat. I'll do my best to monitor it, especially when Ryan's talking, and then I ask Ryan to just let me know if I miss something when I'm talking. So today, super quick recap, we're going to show a little bit of Monte Carlo. We're going to show the OpenAI gym that you can do for reinforcement learning, and then play around with SARSA and Q-learning algorithms. So reinforcement learning, right? We're talking about an agent. It's an uncertain environment, and the only thing we're getting is this scalar number reward signal. So we model these guys as Markov decision processes, and the reason why we do this is because at any given time, the state that you're in, don't care how you got there or whatever. So when we talk about the value of being in a particular state, or the expected value, the value of a state and an action, that's all you need to know, is that you're in that state. You don't need to know how you got there or anything else like that. So that allows us to do that kind of modeling. And in terms of the notation, we won't be doing a whole lot of the theoretical notation, but we do tend to talk about V as the value function for a given state, and Q as the value function for being in a state and taking a particular action. So we have the Bellman equations that underlie some of the work that we've done, just that says that, hey, the value of this is equal to the reward plus the discounted future value for everything that happens after that. Because what we care about is the long-term return, not just the immediate reward for one step. And so we've seen that we can do this policy iteration type thing where we estimate what the value of our current policy is, and then we try to improve the policy a little bit, we tweak it, and then we can re-estimate with that tweak, what is the new value, is it any different? We keep tweaking, and then ultimately there's theory that says we can converge on an optimal policy. So then we started talking about how can we actually use these? What are algorithms that will actually do this? So the first algorithm we're going to look at is Monte Carlo. And this one, at a high level, is fairly easy to explain. When you actually implement it, there's a bit of details. So at the high level, the Monte Carlo algorithm says, just go and, if it's a game or if it's whatever, assuming it's episodic, just go and play it a bunch of times. And each time you do it, just look and see what the overall return was. So not just the immediate reward, but the whole sequence of rewards, what the return was from any given state. And you do this a bunch of times. And so if in state 6, you have passed through there 3,000 times, just average what are those 3,000 results. That's the super simple version of Monte Carlo. You just do everything over and over again. And one of the tricks in these algorithms is you have to make sure then that you're passing through all the states a lot of times. You can't only be doing the certain states over and over again. Then we got the temporal difference learning, and so we'll get to that later, but we'll look at the SARSA algorithm, which says instead of waiting until you get to the end of the episode and saying, what was my return, we're actually going to do an update after just one step. And so you're in a particular state, you take an action, you look and see what's the next state you're in and the next action you're going to take, and then you use the estimate of the value of that next state and action, and you add your reward to that, and then that's what you use to update the value of the state that you're in previously. And if you make a slight tweak to this, then you actually get the Q-learning algorithm, where instead of actually, once you've taken an action, you wind up in a new state, in this case S prime. Instead of then saying, I'm just going to use the value, the estimate that I have from that new state and the action that goes from there, I can actually look at all the different actions from there. And then I can just take the maximum if I'm trying to actually have an optimal greedy algorithm. So these three guys, Q-learning, SARSA, and Monte Carlo, are the three things that we're going to look at today. All right, that was hopefully as promised, very brief. Any comments or questions before we dive in and start looking at some code? All right. So first up is Monte Carlo. And so this is an example that's actually in the book. So already on our book club repo, there's a link to this GitHub repo that has Python examples for many of the things in the book. And so in particular where there's a figure and it's like, hey, how did they get figure 5.2 or something like that? Then there's actually code that will then produce, those figures. So this blackjack Python file that's in the repo, all it does is it creates the figures that show what the optimal policies for blackjack are. And it uses different versions of the Monte Carlo algorithm. But it wasn't really set up as a demonstration of the algorithm itself. It was just, here's code that actually does it. And if you pore over it, you can kind of figure out. So what I'm doing is I'm actually using a lot of the helper functions that are in that blackjack file. But what I did is I took the code for Monte Carlo exploring starts and I kind of put it into this Python, this Jupyter notebook, so that we can kind of go through it a little bit easier. So in terms of this code, I've got a couple imports in here, standard packages. Blackjack is the name of the file that's from the repo. So here I'm importing all the helper functions. And then we've got some global variables we're defining here. You guys want me to make this a little bit bigger? So in blackjack, in any state that you're in, there's only 2 actions you can take. It's a very small number of actions. You either take another card, which is called hitting, or you stop taking cards. You do stand, and then that means it's the dealer's turn, and then whoever's closer to 21 without going over wins the game. So in this game, hit is represented by 0, stand is represented by 1, and then we're not going to really worry about policies too much in here, so we don't really need to worry about some of this policy representation. So here, ultimately, is the Monte Carlo algorithm. And the reason why this is a little bit more complicated is because we're doing 2 things here. One thing is we have to have a behavior policy, that's our exploring starts policy, that says we're going to try out all these different situations so that we can see all the different states. All right. But then at the same time, we're going to have a target policy, which says, what is actually the best thing to really do in that situation. So we need to keep track of both of those things when doing Monte Carlo. So the first thing we see here is it is representing the states and the actions. So this is basically our Q function here. Okay. Typically, we think of a state action as a pair, so it would be 2 numbers. But in this case, the state they are representing as 3 numbers itself. They didn't just sort of multiply it all together, mush it all together into a single number. So they could have just said 200, 2. Okay, 200 states and 2 actions. But they left them out separately. And so basically, there's 10 possible numbers that you could have that are interesting numbers from 12 to 21. All right, and there's 10 different numbers that the dealer could be showing, 1 through 10. And then if you have an ace that can be either 1 or 11, so I don't know if all of you guys know the blackjack game, but anyway, so that's the last thing here, which is yes, no. Do I have what they call a usable ace that can be either 1 or 11, or at this point, are all the aces used up? They're all 11s. So that's our state, is what do we have, what does the dealer have, and do I have an ace that I can make either 1 or 11? And then again, just 2 actions. What we're going to keep track of basically is the amount of return we're getting from each of these situations, and then we're going to count how many times we've been in that situation, and we're going to calculate the average. So basically what you'll see in the Monte Carlo algorithm is that we're going to take our values and we're going to divide it by our count, and that's going to be the estimate of how good the returns are for any given state in action. All right, you guys with me so far?
Yep.
All right.
Pretty good.
Thank you. So we have this behavior policy. I'm not going to go over that right now. And so basically what you'll see for the main Monte Carlo algorithm is we're going to predefine the number of episodes that we want to train for. So 1,000, 10,000, 100,000, whatever. And so then we just have a giant loop that says we're going to play this game, this blackjack game, episode number of times. That's the outer for loop. Okay. We will pick a random starting state. So for some reinforcement learning problems, it's not that easy. For blackjack, it's actually pretty easy. You can just say, hey, I'll randomly pick what number you have, and I will randomly pick what number the dealer has, and I'll randomly pick whether or not you have an ace, and that'll just be your starting state. Okay, it's a little bit more complicated if you're doing, say, self-driving car to figure out what is the initial state. You can't just sort of, randomly pick things. You have to have a road. There's rules to, the cars around you, how fast are they going, all that stuff. But for blackjack, it's very simple. So we're not really dealing cards per se in this simulation. We're just saying, boom, you happen to be in a situation where you have 15 and the dealer has, whatever, a 7 showing. You don't have an ace. What are you going to do? Okay, that's what this initial state does here. So from here, we're going to choose an action. They're using random, okay, to just basically, again, we want coverage for our behavior policy. We want to just, try out all these different things. And so then at this point, what we're going to do is we're going to play the game, all right, and because the game can have multiple turns, we actually, blackjack's a relatively short game, but still you can take cards multiple times. And so the proper Monte Carlo algorithm is keeping track of every state that you see between when you start and when you get to the end of the game, when you get to the end of the episode. So right here, this call, blackjack play, okay, that's what's in the helper file. That has the rules to the game of blackjack for when over 21 you go bust, and the different cards and things like that. Okay, so this part, this is basically your environment. Okay, this is saying, hey, I'm in an initial state. I'm going to do this action. So I'm in an initial state of I have 15. My action is hit. I want to take a card. Now go and play this game. What that's going to do is it's going to return a trajectory, and it's going to say, what are all the steps that happened between where you started and when you got to the end? And so in the full Monte Carlo algorithm, you're not just taking your initial state, you're actually, it would be very, Ryan introduced the term a couple of weeks ago, it would be very sample inefficient if you only updated based on the initial state. You're passing through multiple other states, so you want to update on all of them. Okay, in this case, we are implementing a version of Monte Carlo that's the first visit version. So I don't think in blackjack you can actually repeat, wind up in a state, again, but in lots of other games you can wind up in the same state later. So in Pac-Man, you go whatever, you go right, you go left, and you're back in the same spot or something like that. But so in this case, the math is slightly different. You can do it either way, but we're only going to update the first time that we've seen a particular state. for this given trajectory. So we play the game and we get a trajectory back that says, let's say there were 3 turns and then the game ended. Okay, so then this for loop is going to say for each of those 3 turns, we're going to potentially update our value estimates. And what they're going to do is they convert the values of the cards and whatever into our state. And so this guy here, state action, this is what we need to index into the Q table. And so basically what we do is we say, hey, if we've already seen this state action pair, this is not our first visit. In that case, we're just going to break out of the loop because we're only updating the first time. And after that, we set that we've actually been to this state in action. And here's where the real math is. This is the only real mathy part of the algorithm. Okay, it says for our value table that has, again, 1 entry for each state and each action, just add to it the amount of reward that we got. And for the table that keeps track of how many times we've been there, add 1. All right. So now technically, just, this simplified implementation, this is off by 1. So they initialize this as 1. And so when you've played the game 5 times, this is actually a 6. And so it's slightly doing the math wrong, but they didn't want to handle division by 0 errors. And so they just, simplified it. But so technically speaking, if we've been through this state action pair 1,000 times, it's dividing by 1,001 instead of 1,000. But that's good enough because we're going to do like hundreds of thousands of simulations. But this right here, this is the Monte Carlo algorithm. We needed a bunch of for loops and stuff wrapped around it, but the algorithm itself is fairly simple to describe in terms of, hey, what is the average of doing something a bunch of times? Well, you sum up all the return reward signal that you got, and you divide it by the number of times. That's our algorithm. Okay, and so you can see here it takes state action values and divides it by the counts. And so this, when you divide those two, then that's basically your Q function estimate. All right. Pause here. Any questions?
Where are you setting? Where are you setting the reward?
So the reward comes from the environment. All right. So when we say play, it's actually figuring out what the reward is for that action, and then it actually keeps playing until it gets to the end of the episode. And so this is actually returning a list. This is returning a trajectory, which has basically the list of the states, the actions, and the rewards that we got.
Okay.
So I didn't really go into detail about that, but this guy here is a list, which is why we can actually run a for loop over the variable trajectory because it's a list. But for each one of the things in the list, it's just simply saying, what was the reward I got from that state and that action that I took? I'm going to add it up, and I'm going to increment the counter that says how many times I've seen that state in action. And so after you do this thousands of times, it's going to say, oh, guess what? You had a 15 and you hit, and when you take all the rewards, in this case, I think it's just +1 for win, -1 for loss, 15, and you hit, the total sum after 1,000 times was -200. And so when you divide that by 1,000, then the average for hitting is -0.2. What happens when you don't hit, when you stand and you say, I'm not going to take any more cards? Well, after 1,000 times that, the total sum was -100, let's say. So that's actually a lousy state to be in because you lose either way. But -0.1 as an average return is still better than -0.2 as an average return. And so the rule says you should stand.
So unraveling some of the details there. So that blackjack dot play, that's some external thing that just kind of executes the whole game, right? So
Yes,
that's
so they hand-coded the rules to the environment. They hand-coded the rules to the game of blackjack. And that's why I sort of separated this part of it from the rest of the file, because theoretically, if someone's kind enough to create the environment for you, you don't need to know anything about that code other than that it's
Mhm.
debugged and it's correct.
And so your input there, the current policy is what tells it what action to take, right? While it's doing that exploration.
So
And
yeah, so you're actually telling it the first move, but if there's moves after that, it's actually going to follow the policy.
okay. Um, and then in that loop, it's playing you against the dealer with some standard operation like they would in the casinos, right?
Mm-hmm. Yes, and this may not exactly match, like casino rules, but
Yeah.
the standard game of blackjack basic rules.
Mhm.
So usually it's like up till 17, the dealer, takes a card, and then 17 and higher they stop. If the rules were slightly different, you could program them, and then you could see what the right policy is against that set
Yeah.
of rules.
And so the stuff that it's returning a reward, and that's just a single score. They won or they lost, right? But the
Mm-hmm.
trajectory, that's a list, and that's saying the history. So it's saying we were in this state, we hit, we were in this state, we hit, we were in this state, we stood at that point, or we bust, or whatever.
Yeah, so you can imagine if this was chess, it would be a much longer trajectory. It wouldn't be length 3, it might be length 70.
Mhm.
Here's all the different moves. You can see why Monte Carlo would be then problematic in terms of solving chess. Not only is there a super large number of states, but it's really difficult to assign credit to my move as to whether or not I won or lost the game 70 moves later.
Mhm.
You know,
And so in that for loop where you're iterating over trajectory, what you're doing there is you're essentially saying we had this, and this, and we took this action in terms of the state. So like we had to use place, or we didn't. We had a certain player sum, the dealer had a certain something. Um, and then we take this action, and then you're putting that in the state, and you're applying the reward for the full end of the game. So it was only the first hit call, but you're giving it a reward as if it won, even though that
yeah,
wasn't necessarily the winning move. It just led to it later.
yeah. So they're using undiscounted rewards here, and there's a shortcut here because they basically know that the rewards are all 0 except for at the very end when you won or lost the game. So they're doing a little bit of shortcut here. The full Monte Carlo algorithm, what you would see is they'd have to be multiplying the discount factor times the number of steps away the game ended. And so if it's 3 steps, then really this technically should be like gamma cubed times the final reward. And then plus gamma squared times the reward from, the step before that, which is 0, plus gamma times the return from the one that's, before that, which is 0. So they did a real shortcut here just to speed things up. So yes, so in this case it's undiscounted and the others are 0. But if this were return instead of reward, if somebody had calculated it for you, the discounting and all that, then you can really just simply say, I'm just going to add the return and I'm going to add 1 to my counter, how many times I've been here. And that's all you do at the super high level. That's all you do is you say, I sum up my returns, I count the number of times I've been there, and my average is just the sum of the returns divided by how many times I've been there.
Mm-hmm.
And it is fine that for first steps, the average won't be actual average.
You talking about my
it
off by
bothers
1
me.
thing, or?
Yes, it bothers me.
It bothers me too. That's why I mentioned it. I debated mentioning it, but the reality is, we could change the code to initialize it as 0. And once we've been in every state, we won't have any division by 0 errors.
And the
So yeah, a few ifs would fix it, but yeah, it will make code more complicated.
Yeah, and then they could have made it slower, but what they could have done is instead of initializing to 1, they could have initialized it at least to like epsilon, like 0.0001 something, right? Then that would avoid division by 0 without being off by as much.
Well, it will make it, you know, too big, and we cannot check it out actually when we already have the number. So it will be way off this way.
Yeah. But again, we're assuming if we're actually solving this game, we're finding the optimal policy, we're going to run it a gajillion times. And so at the end of the day, we could have just initialized it to 0 or whatever, but that's going to go away. That's anyway,
you really
that's definitely not the instructive part about learning the
yes,
algorithm.
I
That's the
understand.
coding.
Okay.
The coding details.
But purely theoretically, it can happen that we will never be in some particular state. The probability of it is very low, and it, you know,
yes,
drops.
Yes. So we are like uniform random choosing our starting states and our actions. So the theory says if we do this infinitely many times, then we will visit every state action pair an infinite number of times.
But infinity does not exist.
Yes, that's why in practice you could have a very, very small chance of never having been there.
And one, not that it's really important, but ultimately that's not going to change your policy in the end, because all of them are going to be just divided by +1. So in the end, the policy choices are all going to be the same. It's just the value is going to be off by some tiny amount, but they're still all going to be scaled by the same amount. So it's not going to be the difference between should I choose this action or should I choose that action, because their values are all just going to be scaled to 10.
Yeah, in the end, I don't think it's going to make any difference. But hypothetically, if you only visited a certain state action pair twice, then dividing by 3 instead of dividing by 2 kind of makes a difference. But if you visit a particular other one 20,000 times, then the difference between dividing by 20,000 or 20,001 is pretty negligible. Yeah, it's just a little programming thing. So, all right. So I think maybe what we'll do is we'll move on, but we can come back to it. So after we've seen like the Q-learning, you know, the SARSA, if that raises other questions, we can kind of compare them. Okay, but I don't want to get too hung up on this. So again, the kind of funny thing is that Monte Carlo, the concept is pretty simple. Just play it a bunch of times and what's the average? So, you know, of all the times that you had whatever 16 and the dealer had, you know, a 3 showing, what was the average? You know, that's all the Monte Carlo algorithm is saying to do high level, but you need a whole bunch of code in order to sort of implement the nitty-gritty details. So so what we want to do next is we're going to take a look at SARSA and we're going to take a look at Q-learning. Those are not going to be examples from the book. There's going to be something I worked up, and I actually used one of the pre-made environments in OpenAI Gym to do that. And so so first what we'd like to do is we'd like to actually introduce the gym to you. And so I'm going to stop sharing and I'm going to pass over to you, Ryan, to go ahead and do that intro.
So just to start off, I want to give a little preamble about the OpenAI Gym. This is sort of the environment paradigm that a lot of reinforcement things are built on. So OpenAI Gym comes with a whole bunch of different environments and games that you can play with, but even beyond that, almost everything is built on the assumption that you're kind of working with something that follows this format. So there's a whole bunch of libraries like stable baselines that implement a whole bunch of the algorithms that we're going to be looking at. They assume that you're laying it out like this. So this is a fairly core thing that is good to understand. And so let me give a link to this just in case. So I put together a notebook that follows along with their documentation. And I just want to point out that if you want to look at this in more detail, there's this whole thing on the documentation. So I'll give a summary of it, but if you want a deeper look, that's the link to it. So I set up this notebook, and basically it's just running through the basics of the OpenAI gym. And so I start off and I just install the newest version of the gym. And all you have to do, pip install gym if you already have Python installed. And then I just import it. And then making an environment is really simple if you're using one of the ones that's already been prepared. So in this case, I just say gym.make, and then it makes a taxi environment, which is a specific game that they have in there. And so we won't get into how to make your own custom environment, but it's a fairly simple thing to do. I worked on that for, there's a, what's it called? It's essentially Snake, if you're familiar with that game. There's a Kaggle competition going on right now. And I kind of transformed that game into a gym environment, and it's not really that hard. You just have to basically say, how do I convert this to match the formatting of the OpenAI gym? And so the first thing that you typically do is it's a little bit unintuitive, but you reset. And essentially what that does is it prepares the environment and it makes it the initial state. And so that can be like, if you have chess, imagine that's preparing the board and just showing you, here's the position of all of the pieces. And then it's giving you that observation to tell you what's the state and what actions can I take and stuff like that. And so a pretty common thing you'll probably do is you just iterate through time steps of a game. So you have something and you're playing chess, you're playing whatever else, and you're taking a whole bunch of discrete time step actions. And so you can do render, which will actually draw out the board. It depends on exactly what environment you're using. Some of them use fancier stuff where you actually have a video that will output. Sometimes you just have simpler stuff like this. It's just text-based, and you can have all kinds of stuff. And so one of the core things, this is similar to what we saw in Ted's example, is you can take a step, which is basically saying, okay, I'm giving you the action that I want to take, and then it's handling all of the internals for you. You don't have to say, like, if I choose the action, go left, you don't have to code and say, okay, I'm changing state to go to this other thing. The environment is actually handling all of that, because sometimes your environment can be some really complicated game and you don't actually know how to manipulate it. You just know how to send it actions. And so one of the simple things you can do is you can look at the environment and look at the action space. And so the action space is essentially just telling you, here's a list of all of the possible things that you can do. So in this game, in the taxi game, you have 6 different options. You can go left, you can go right, you can go down, you can go up, and you can drop off, and you can pick up. And so the goal of the game is you're just this taxi and you're trying to you have to pick up the person and then you have to take them over there. And so it's fairly simple, but you have to choose the correct actions and you have to try to do it efficiently, because you're penalized every time step -1 point. So you're trying to take the shortest path. And so this is a simple usage of the library to just play random games, basically. So similar to what Ted was talking about in his game, you just sample from the space. You're just doing completely random actions, and eventually you see a whole lot of different occurrences. And so this is 10 steps of the game of it just doing random movements, and it also tells you what action it was trying to do. So in this case, this is the initial state, then it went east, and then it went south, but it didn't go anywhere because it's already at the bottom of the play. Then it tried to do pickup, but it didn't have anyone to pick up, and did pick up again, and then it went north, and so opened up a space. And so that's kind of the structure of that. And so I glossed over some of these and I'll explain them in more detail now. So one of the core things about this is the observation. So every time that you reset or take a step, what happens is the environment returns you an observation. And the observation is what we would typically think of as like the state. It's basically telling you this is what the board looks like, this is what is happening in the game, basically. And it's giving you the full set of information. And so that can be different in a lot of different things. So people have done stuff in Atari where it goes, okay, the observation that we're giving you is just the raw set of pixels of the frame. Or it might be, here's the position of all of the pieces on the board and stuff like that. So the observation can be whatever is best to represent the game. And sometimes you might have to convert it to a different format, even from what the game gives you. And so then there's the reward, and this is similar to what Ted's been showing all throughout. That's just a number saying, did you get more points? Did you win the game? Did you lose the game, etc. It's just returning a number. And then you also get a Boolean saying if it's done or not. And so this is just kind of, if we look at this for loop, it's going to stop at 10 steps, but your game might not be done. So what a lot of people do is you'll do a while loop where you just say, just keep playing the game until it's done. And so that doneness check tells you when to exit that while loop when your game is completed, and then you can go play another game or do something else. And then there's also the info dictionary that's returned to you. And this kind of just depends on the game. There's all kinds of different stuff that it can return for you. Some games will tell you, you just tried to go left and you were already hitting a wall, so that was an invalid move. Or it could tell you, I don't have any more examples, honestly, but it can tell you all kinds of different stuff. So walking through this in more detail now, so you start, and upon resetting, it gives you just the observation. It tells you, okay, this is the state of the board. This is right at the beginning. And then this is kind of a typical flow that a lot of people do, is you want to do a whole bunch of games. And so you just do a for loop. And so I just did it for only 2 because I didn't want to print a whole bunch of stuff out. And then I'm going through 10 steps. Again, just for brevity of what's being printed out, and then sampling from the action space, and then taking a step and using this action. And then you can see here are all of the pieces that we were just talking about. So the observation is, what's the new state of the board after you just took that action? And then the reward saying, did you get any points for anything? And then the done and the info. And so one of the core pieces around all of this is the action space and the observation space. And so there's various different kinds of spaces that you can use for all of the different things. And you want to do something that logically makes sense for whatever you're trying to do. So there's the discrete space, which is basically there's a certain number of positive integer options. So for example, we have the options left, right, up, down, pick up, drop off. That can be represented as discrete, and you can just say, okay, here's 6 discrete actions that you can take. And so these representations, the spaces, can be valid for both the action space and the observation space. So you might have certain observation things that have discrete representation, or they might have continuous representation, or they might have any number of different things. It goes both for actions and observations. And so previous example using discrete, you could have something that's continuous. So like a continuous action, you could say, okay, instead of going 100% left, I'm just going 0.5 left or 0.25 or any range of values. And then there's this concept of a box, which is kind of important just because very often with these things we talk about boards. And so what this kind of gives you is I want some board layout that's n-dimensional. So you could say I want a 4x4, and then I want it with values in between -1 and 1, and you're playing some game where you want to land on all of the +1 spaces or something like that. And so you can lay that out with a box that basically just gives you that representation. And I've also seen that used pretty frequently for like images. So if you have something that's like an Atari screen, you can represent that entire image as a box, and you can say, okay, here's a 64x64 image, and all of the values are between 0 and 255, and that's all of the pixel intensities for that 64x64 image represented as a box. And then there's the possibility of multi-discrete. So you can have multiple different things that you're making a decision about, but you might only have one specific option that you're able to take of that grouping. So I don't have a great example of that off the top of my head. But the other option is multiple binary. So you might have multiple things that you're making a decision off of, and you can do multiple of them. So you could go left and go up, for example, at the same time. And so this is just kind of exploring, here's how you set all of these things up. So for example, here's setting up a box space. And so we're saying that the lowest value is going to be -1, the highest value is going to be +1, and then the shape will be a 4x4. And this isn't filling any values here. This isn't initializing an array. It's not doing anything. It's just saying, this is the shape of our action space or our observation space. This is what it's going to look like potentially. And then later you might have something that actually fills that in. And so this is the box. The discrete is very simple. You just say like 4, or in our case, we were looking at it before, it was 6. So we have 6 different discrete options that could be taken. And then the multi-binary, same thing. You're just saying there's 4 different actions, and you can take 1 of them, you can take 4 of them, you can take 0 of them. You can do any combination of that. And then this is the multi-discrete, and it functions almost identically as the regular discrete. So I could, for example, I could go in here and I could say 4. And so now the multi-discrete and the discrete function completely identically. But the further step with the multi-discrete is you can add in a tuple, and then it will actually say that there's potentially 4 different actions that you're taking, and each of those has 3 options or something like that. And so that's the distinction between discrete and multi-discrete. And so just exploring the environment that we were already given with that taxi environment, we can introspect that, and we can say, okay, we learned about these types now, what were we actually looking at? And so we can see that the environment had an action space that was discrete with 6 different options. And then looking at the observation space, this one was a little bit confusing to me. So the environment, its observation space, they set it up to be discrete 500, which is kind of bizarre because I would have thought that they would have set it up as box, because this looks like a decent box layout that could have a few different values inside of it. But they chose to do it as discrete. I don't exactly know the reasoning behind that, but
I can tell you about that one, because the upcoming example is the taxi problem, and so it's just they used XY coordinates, and then also there's where the passenger is and where they're trying to get to, right? So basically where the taxi is a box, but where the passenger is and where they're trying to get to is not necessarily. And so that's why they just did it slightly differently.
Yeah.
So it's a whatever, it's a, I can't even remember, a 5 by 5 by whatever, 4 by 6 set of possibilities. And I guess they could have done that as a box. You can have different dimensions, right?
Yeah. So my thought potentially is you do, so I would do something that is like, just copy that. So what I've seen in other things, I don't know if there's any argument for one way or another, is you could just do this as like, I don't know exactly what the
Okay.
Basically what I would do is I would say I have a 5 by 5 grid that I'm operating in, and there can be 4 different things that are laid out there. Maybe my number's wrong there, maybe it's 5 or 6, but basically you would just say, okay, a 0 is the starting position, a 1 is the whatever else, and then I guess maybe you'd have to have something for the walls and the other stuff too. But essentially I would just encode it as a box and then have all of these different things be different integer values potentially.
Yeah, sounds like actually that might have been a better way to do it. I actually ended up writing a little function that decodes the 500 values into the X, the Y,
that's
what the passenger is.
Yeah, that's what I've seen in all of the, because I've seen other people have to do that in Kaggle competitions too, where they go, okay, we've been given it in this weird vector format and now we have to reformat it into an image and place everything on the board essentially.
Okay. Cool.
Any questions, thoughts on any of these things?
So I'll show an example. It'll be a little more concrete, but that open AI gym exists, and that then anybody else who decided to build anything sort of made it backward compatible with OpenAI Gym is wonderful, because it's really standardized the way everybody does stuff. So even stuff that's not from them kind of all looks the same, where like, right, you're going to have an environment and you're going to call reset and then you're going to take steps. So it's really great that they open source this, and also people can just contribute new environments, new games, new things.
Mm-hmm. Yeah, and so just an example of this. I don't know if you're showing stable baselines in a second, but there's this library that I've used in the past. Stable baselines is the TensorFlow version, and then stable baselines 3 is the PyTorch version. And essentially, you can see that they're creating an environment kind of similar to the way that we did, just saying this is we want to play Pong, basically, and then the stable baselines gives you an option for which algorithm you want to have implemented, and it just kind of does the whole thing for you. You don't have to do a whole lot there. But then when you want to actually play the games and learn from it and everything, you can just do this whole create the environment and reset it and do the steps through the games and visualize all of the stuff that's happening. And it follows this exact same paradigm that was laid out with the OpenAI Gym.
Yeah, cool. All right, so let's take a look. Here is here's an example of the same taxi problem that Ryan showed, and we're going to use SARSA to find the optimal policy for this. This is a fairly straightforward thing. So there's a 5x5 grid, and you can just go in the 4 directions, up, down, left, right. But there are certain places where there are walls. So you can't, like Ryan said, you can't go left from a certain place because there's a wall. And they've created these 4 spots on the screen, and randomly, when you create a new environment, randomly you will be in a random place, and the passenger will be in one of these 4 places randomly. So what you need to do is you need to go up, down, left, right, navigate over to where the passenger is, then do the pickup action, then go up, down, left, right, and go to the random location where they want to go to. And then you, once you navigate there, then you do the drop-off action. So like Ryan said, there's 6 total actions. Now, if you think about this really hard, you'll find out that there's certain things that are actually in the 500 states. There's certain things that are impossible. So for example, the passenger can't actually be in location 1 and want to be dropped off at location 1. They're always dropped off at a different location. So there's actually, it's technically not a full 500. There's actually a couple that are impossible. But nevertheless, that's the gist of the game. So let's go through the code. And funny enough, even though this is a more advanced algorithm, the code for this is actually easier than the Monte Carlo. All right. So as Ryan showed, we're importing Jim. I already had it installed here. And if you run this on Google Colab, Jim's already installed. You don't even have to do the actual install. All right. In our algorithm, we have some hyperparameters, okay? One of the parameters is gamma. That's how much we're discounting future rewards, okay? One of the parameters is our learning rate. That's alpha. And then we're going to be doing exploring. We're going to use an epsilon greedy exploration algorithm, so we need to know what this epsilon is. So 10% of the time, we're going to take a random action instead of the best action we have. And then when we take that action, we're going to get a reward signal. We're going to use that to do an update. And we're going to actually have a fairly aggressive update. This 0.2 is a very large number. This is not a typical alpha that you would use for a complex problem. So we're going to say we're going to take 20% of that, and we're going to update our estimate of what is the value of a particular state action pair. I'm initializing some counters here just to keep track of things. And so I've got some helper functions here. So you can see here actually is Ryan, where I take the state number that's like, 0 to 499, and I actually figure out, oh, I can return a string that says I'm in row this, column that. Here's where the passenger is. Here's where the destination is. So I did that, but I'm going to skip over these for a second and just go down to the main algorithm.
Not to burst your bubble, but there's actually a decode that's into the environment. So you could just do inf.decode and it would probably give you a similar output.
All right. Good. So I learned something about Jim today. All right. There is some extra code in here because I'm actually going to show different metrics. Okay. So when you see this code here that's like counting cum this and counting all these things, that's because I'm calculating these metrics. So I'm going to not really talk about those too much. All right. I want to just talk about the main algorithm. So the main algorithm is relatively straightforward. It says, I'm going to run for a certain number of episodes. Okay, we've predefined the number of episodes here as episodes. And for each one of these, I'm going to start out in a random state by calling this env reset that Ryan showed us. All right, and then one of the things that it returns is a done variable, right? So we're going to say while not done, we're just going to keep playing until this episode ends. In this particular case, for this sample taxi world, they built something into it that if you haven't dropped the passenger off by the time you got to 200 steps, it just ends the game. All right. You might see in certain other code, it'll say something like, hey, if you've gone this long, abort and just start over again, something like that. But we don't need to do it because it's actually built into the taxi environment. And so what we're going to do here is we're going to say we're going to take one step, and that, of course, is going to give us the new state, the reward, and whether or not we're done. Okay. And in this step, we have to pass in certain information. So what is the current environment so that we know what the state is? What is our Q table? So these are our estimates for the value for every single state action pair. All right. And it's going to loop over this until it's done. And then when it's done, then that's the end of that episode. There's a bunch of here stuff again that's just tracking things. Okay. And then it's going to loop back. So this is the outer training loop here. You can see that if I didn't have all this other code that's keeping track of things to produce various statistics, it would basically just be for a number of episodes, while not done, take a step. That's just the outer loop. So the real work is happening inside this SARSA step function. Okay, and because this is temporal difference learning, we update after every step, so we don't have to have any special code at the end of an episode. We had all that special code for Monte Carlo that then looked at the whole trajectory and looped over that. Actually gets much simpler here. All right, so let's go to the SARSA step. One other thing about this environment, so I think I think Ryan said there's a -1 on every step. I can't remember if it's 0 or -1 for each step, but if you try to do a pickup in an invalid location, you get this big negative reward. You get like a -20. And if you try to do a drop off in an invalid location, you get a big penalty. You get this -20. So that's one of the things in this code that's actually tracking is this thing called penalties. It's any of the, how many times did you get that big fat -20? Okay, so clearly it's an avoidable situation. We don't want to do those. So what does our SARSA step do? It says we're doing an epsilon greedy action here. So we pick a random number. If it's less than epsilon, we are going to randomly sample. Okay, so this is taking advantage of the built-in GIM functions here. So the env action space tells us what are the possible actions, and the sample function is uniformly going to pick a random action from the action space. So that's epsilon % of the time. 1 minus epsilon % of the time, we are going to pick the action that has the highest estimated return. So that's the greedy part. So we know what state we're in. We know what action we're going to take. Then we do env.step, telling it what action we're going to take. So again, this is OpenAI GIM. We don't have to write any code for this. It's going to just do it for us. And here's the what Ryan showed us. These are the 4 things that function returns. So we know what state we started in. We know what action we took. We now know the next state. So for SARSA, the next thing that we need to do is we need to pick our next action. Okay, so here we see this same code again that says for epsilon % of the time, we're going to pick a random action. For 1 minus epsilon, we're going to be greedy and take the biggest estimated value. So based on that, we now have our next action. So that's what we need for the SARSA algorithm. We need our old state, our old action, and then we need our next state and our next action. For simplicity, we have a variable here that says, what is the estimated value for the next state, the next action? So we look up in our Q table, what is the value we have for the next state, the next action? This is the temporal difference update function. Okay, so the new value is mostly the old value. 1 minus alpha times that, plus alpha times our reward plus the discounted gamma times the next value. In the book, this is shown slightly different, even though mathematically it's the same. What it's shown as is the new value equals the old value. So this is the full, which is 1 times old value, plus alpha times this new thing here minus the old value. So the difference between the new value and the old value. Mathematically, they're the same. It's a little bit faster to calculate it this way, but just in case you're saying the formula looks a little different, but that's why. So it just simply takes the alpha times old value and moves it over here. So again, this is mostly, especially if you imagine alpha being some number like 0.01, 0.001, this is mostly the old value, but we're going to take a small step based on the learning rate towards our new estimate, which is the actual reward we got. This is the new info we have. This is the only new info that we have, which is the reward we concretely got when we took this action. We add this reward to the discounted estimate we have from the next value. This estimate is just based on our Q table. It's not coming from the environment. This reward is the only thing coming from the environment. So once we have this new value, then we just update it. We just stick it into our Q table. And that's the temporal difference update. So I'll pause here. Any questions, comments? All right. So this is an on-policy algorithm. So we are going to be doing this epsilon greedy algorithm that says the environment will automatically initialize us into a random starting state. We will continue to take actions mostly greedy, but epsilon% of the time, in this case 10% of the time, we'll take a random action because we need to explore all possible actions. If we start out by going down, or south, I think it calls it, and we get a positive reward, then we may never find out what would have happened if we had gone north or east or west. Maybe we would have gotten an even bigger positive reward. So that's the reason for the epsilon greedy. All right, there's a few other helper functions I showed. Here's one I wrote that figures out the state. Keep track of the number of penalties. Those are just kind of bookkeeping things. They don't really have to do with the algorithm. So
there's one question related to SARSA, basically asking if SARSA is a well-defined algorithm, is it not part of some library?
So I don't think OpenAI Gym actually has any algorithms. I think it just has environments.
There are, but I think it's a separate library.
It's a separate.
The stable baselines is supposed to be like an extension. They might call it open baselines or something like that. I'd have to find it. But I do believe that they might actually have it in there. I can find that.
Yeah, and even if there aren't official ones, I'm sure there's people with just GitHub repos that implement various algorithms. Like I said, OpenAI Gym is just wonderful because even if you don't want to just use it by itself, it's become the de facto standard, and so everybody just programs to that standard. So you're always going to have an environment reset, environment step, blah blah blah. So yes, I'm sure somebody must have implemented it, but in my very cursory search, I just didn't run across that. And so this is, I think I found some code or whatever, but I mostly just coded this up from scratch.
Yeah, because all these are standard algorithms and pretty much they are hard for the common person. So anyone trying to build applications or something, then they can just use those as library calls, right?
Yeah. So these are actually basic algorithms that you don't see implemented because the fancier ones are better. So actually, like Ryan was saying, if you want to do TensorFlow, you can use stable baselines. If you're doing PyTorch, do stable baselines 3. I looked at stable baselines 3, and this is the tabular version. So we're not using any neural networks. We're not estimating. We're just literally creating a NumPy array as a table that holds our estimate for every single state, because there's only 500 of them. Okay. And nobody programs those because for all the real world interesting reinforcement learning problems are too complex. So stable baselines does have a deep Q-learning algorithm where it actually uses a neural network and it estimates. But it doesn't have the base Q-learning algorithm because they just assume the problems you're working on are much harder, and so they have the fancier version. But that's a good question. So maybe at time we'll see what other algorithms are actually out there, and maybe there's some good repos that say, oh, here's a bunch of different, including not the super fancy ones, but some of the more basic ones.
Have you see implementation with upper confidence bound?
I think you had mentioned this before. So upper confidence bound, I haven't really seen anywhere, because for like multi-arm bandits, it's relatively easy to calculate the confidence bound, but I think it gets trickier when you're doing more complex problems.
More
right?
complex reward, yeah.
So
But still,
if
it
you,
could be done. What is, you know, it will be more complicated, yes. What is actually, okay, what is actually interests me much more, there is a better algorithm, which is called Thompson sampling, but I cannot imagine how it could be implemented here.
Yeah, I'm not sure. I mean, ultimately, it's kind of like when you do hashing, right? When you do hashing, you can get collisions, and you can have different keys that actually hash to the same value, right? So if you're estimating and you've got a neural network, even if you have multiple different states that all sort of, go through the neural network and map to the same sort of output value, you could theoretically just sort of treat them with the same, confidence interval. I'm not sure.
Well, confidence interval is for average value for the reward, so you can compute it in this sense.
Right, but I'm saying we're no longer in the realm, when you get into the real problems, you're no longer in the realm of actually having all the states. You're now just estimating through a neural network what the value is for a given state. You're not tracking the individual states anymore. So it's a little harder to track how many times you've seen something.
With upper confidence interval, you initialize these upper values as, something really big, like 1 million. So right. the algorithm is forced to go through each of them at least once.
Right. No, what I'm trying to say, Maya, is to update your upper confidence bound, you're basically kind of dividing by square root of n, right? But we don't know n because we're not actually keeping track of every state.
Yes.
We're using a neural network. So I think you can kind of do it, but it just gets a little fuzzy.
In the algorithm for upper confidence interval, you initialize it not with 0, you initialize it with a very big number, like 1 million. So it means that the reward at first for everything is very high. It forces the algorithm to visit all states.
Right.
But maybe,
so let me just stop you right there.
States.
Let me just stop you right there. So just initializing, forget about even the algorithm, just initializing. How do you initialize a neural network to output 1 million for every possible state input? It's just non-trivial. Like, I'm sure it can be done, but it's no longer like as trivial as when you have the tabular and you just list out every state, and then you can obviously just initialize it. Make sense?
Well, theoretically, it is doable.
Yes. No, and I'm not saying that it hasn't been done. I'm just saying I haven't read about it because it obviously gets a little trickier when you're estimating versus when you have just a nice simple table.
Yeah.
Okay.
But
so
it's helpful, you know, it works better than epsilon greedy, much better.
Yeah. Okay. So let me show you a few things. So so when I trained this, and this taxi problem, it's relatively small. It's 500 states. Okay. And so here's our Q table. You can see I'm initializing to zeros, and basically it's 500 by 6 because there's 6 actions. North, south, east, west, and then pick up, drop off. So we're going to train for, I forget what I set train episodes. It's a relatively small number. So 700, 800, something like that, 700 episodes. So you can see it did some bookkeeping, okay? And it said for the first 100 training, it averaged 200 time steps per episode, and it averaged 16 penalties per episode. I don't know why I, for whatever reason, didn't print out the rewards. Oh no, here it is. Here's the training average. So and sorry, let me go back. I didn't explain this quite right. So this first line is the training averages. This is what happened during training. And then in the eval step, this is now turning off the epsilon greedy. It is fully greedy following the policy. So you can see when it's averaging 200, that's just the built-in where basically it the environment basically, you know, times out. So we start out with this really terrible thing, averaging a reward of negative 300. So yes, Ryan, it's -1 after every step. So it's just wandering around, getting -1s, and then it's getting a bunch of these penalties. And then you can see it's getting better. Okay. So when you're training, this is one of the things that you can monitor. You can certainly monitor how is my average reward doing. And in the case of something that's like epsilon greedy or something that's off policy, you have to differentiate what is happening during the training when it's exploring versus what is the optimal policy that you're actually trying to find. And so I purposefully printed out this way with training and eval because this reminds me when I'm training a neural network where I have my training set numbers and I have my validation numbers. Okay, so we train for 100 steps and then we pause and we actually just run based on our fully greedy based on our Q values at that point. Okay, and so that's a little bit like a validation step. So anytime you have sort of like bad things that you can do, there was the whatever the cliff world in the book where basically, you know, if you fall off the cliff, you get a -200. In the exploring version of it, you're constantly falling off the cliff, but that doesn't mean that your policy would ever tell you to jump off the cliff. And so that's the difference between training and validation. And so another thing that they do in the book, and so I wanted to show this here, is they look at how long are your episodes. Okay, and they're actually showing sort of the inverse of that. So there's charts in the book that say for hard problems. So this isn't necessarily a fit for chess. For chess, you really want to just kind of look at, are you winning or you're losing? But in this case, it's trying to figure out kind of, you know, how to get from A to B. And so the faster it gets there is an indication of it's learned and it's doing something smart. So in the book, they have these charts that show on the x-axis, this is the number of steps that you've taken. Okay. And on the y-axis, this is the number of episodes you've completed. And so initially, this is very flat because it takes you a lot of steps before you complete an episode. And by the way, this chart here, this is steps times 100. Okay, so this number here is 10,000 steps. That's why it doesn't look so bad here, but just remember, this x scale is times 100. So you can see it starts flatter where it's a lot of steps before it moves up the number of episodes. But then it's as it learns, then for the same number of steps, it's doing more and more episodes. So that's another way that you can monitor your training. is you can, if it's this type of problem, you can see if it's actually doing more episodes per step, so to speak, if this is getting faster. Another thing that I did is just in the evaluation, you can see that there's still a bunch of these that time out at 200, and then there's an average that's lower in terms of the number of steps to complete an episode. I have some examples here. I'm going to scroll past these. We're going to train some more. So here I say SARSA train for another, whatever it is, 3,000 episodes approximately, something like that. And so now you can see our reward is improving. It's going from around -8. It's increasing. There's still some randomness to this. It's still, you know, got that explore, it's epsilon greedy, but definitely trending upwards. And ideally at this point, we would have to do it more than just 3,000 times. But at some point, you're going to have tried all different state action combinations. So it's going to know what to do. Now, if you look, this is the same curve, but it's been extended by the additional 2,800 episodes. Now you can see it's in a very linear looking region, okay? So at this point, it doesn't look like it's really learning anymore. It's learned what it needed to learn somewhere around here. And now the number of steps per episode is pretty flat. And so that's why this now looks like a straight line. So there are some of these curves like this in the book. If you look at the average number of steps here, then there's like still one state that we hadn't explored and it got stuck there, but all the others are down here around like 10 steps, 15 steps in order to complete the task of navigating, pick up the passenger, navigate, drop them off. So that's what this notebook does in terms of SARSA. And then the cool thing about Q-learning is that where is it? This is the only line I changed in the notebook. Every other line in this notebook is identical. Okay, so going back to SARSA, for the SARSA step, it says pick a next action. I guess technically it's more than one line, but pick a next action, and then next value equals the Q table value of that next action. In the Q-learning version of it, I don't even need to pick an action. I just say take the max of all possible actions. So in the Q table, next state, I guess this could have said something like this. The next state, all the different actions, just take the max of that. And that's the difference between SARSA and Q-learning. So if we do this, we get the same thing where we train, we get this. We could compare these two side by side and you will see that the Q-learning actually learned a little bit faster. It exhibits that same behavior where, sorry. So then we train some more. If you compare also head to head, you'll see at the same episode number, the rewards average, they look a little better. Once it stops learning, you see this linear behavior. And in this particular case, it's now, because it learned a little bit faster in the same number of episodes, it hit all the different states. That could just be random luck. But so then basically, the worst case scenario, it took 18 steps to complete. If you're wondering why these are not constant, why it's not just one number, is because you get started out in a random place and the passenger's in a random place. So you could get lucky, you could be really close to the passenger, your destination could be really close. And so that's how you could get like a 6 to solve it. But you could get unlucky where you're in the lower right corner and the passenger's in the upper left corner. You have to go all the way up there to pick them up. And there could be walls in between and whatever. So I suspect that the 18 is in fact the minimum number of steps possible. It just got unlucky in terms of what the initial state was. So that's Q learning, and again, pretty cool. I can't remember how many years between SARSA and Q learning, but basically, if you look, I had said that you know, a whole bunch of reinforcement learning today is based on Q learning, and it's fancier versions of this. And again, we have a physical table where we created a NumPy array that has, in this case, 500 states, but you can't do that for really big problems. So next week is 4th of July, Independence Day weekend. So we're going to skip next week. We come back, we'll talk about planning. So people combine planning with Q learning. And then I'm not sure when we're going to get to it, but the other big algorithm that we're going to learn, which comes towards the very end of the Sutton and Barto book, is policy gradients. It does not use value tables at all. It's a radically different, but basically Q learning, planning, policy gradients, those are the only ingredients you need to know to basically know all of modern day reinforcement learning. All right. So we're, as usual, a little over time, but any questions about the actual coding examples? All right. Well, if you guys are interested, I'll get these notebooks linked up on our talks repo, but you can play around with these. You can look at OpenAI Gym, and if you just Google it, you'll see lots of other people also have examples where they've trained things to solve the problems. Just beware. I do think that for OpenAI Gym, like if you look at the sort of like the robots walking, the not the cart pole, because that one's pretty easy, but all the other sort of dynamic physics things, you will see a lot of people have policy gradient solutions to those. For continuous problems, people tend to use policy gradients. And so just know that we haven't gotten to those yet. So if you're looking for examples, you might have to look a little bit just to make sure if you want it to be something familiar, if you want it to be Q learning and not one of the policy gradient examples. All right. Well, thanks for joining us. We have the project discussion next. So I will stop sharing my screen.